The oscillatory dynamics transductive bridging theorem proposes that physical identity is an active, emergent state generated by recursive stabilization. This stabilization is defined by the interaction of two variables. The first is phase strain, which tracks the tension driving a system toward reorganization. The second is recursive coherence resilience, or RCR, which acts as structural memory. Identity emerges from the multiplicative interference of these two processes. Without both tension and memory, the state remains formless. Addendum 20.1 transitions from analyzing stabilization in digital models to testing it in physical hardware. We are moving from the computational 10 series to the experimental 20 series. Because a mathematical framework is only as valuable as its falsifiability, the 20 series provides the physical apparatus required to either validate or disprove these coherence predictions. The 10 series computational campaign applied a Gaussian coherence kernel to 6 classical chaotic attractors. Out of these systems, only the Lorenz attractor showed structural coupling. The remaining 5 systems exhibited effective damping or indeterminate responses, suggesting a limit to the probe's effectiveness. The cause lies in the kernel's functional form. The Gaussian kernel used in these models is mathematically identical to a Maxwell-Boltzmann distribution. This is the signature of thermodynamic equilibrium, first established by James Clerk Maxwell and formalized by Ludwig Boltzmann to describe statistical distributions in state space. A Maxwellian kernel distributes coherence isotropically. This dilutes the energy across the entire state space rather than concentrating it on the specific frequencies required for structural resonance. Furthermore, classical digital attractors have no intrinsic memory variable. Their memory time scale is 0, meaning they cannot retain structural history between steps. Combining an isotropic thermal probe with a memoryless target creates what the paper defines as the double-Maxwellian condition. Probing a target with these parameters results in the statistical, damped behavior seen in the 10 series. These results characterize the thermal limit of coherence gating. Breaking this thermal limit requires a simultaneous shift in both the probe and the target. The 20 series replaces the broad Gaussian distribution with a KF single-frequency probe. This concentrates the applied energy into a sharp spike at a single frequency. The targets are shifted from digital models to physical substrates, like metal Chladni plates, which possess mechanical settling and material memory. This shift from broad to directed systems follows the trade space documented in NASA research on plasma confinement. In that field, Maxwellian approaches like tokamaks are consistently less efficient than directed, non-Maxwellian energy systems. The RCAM He extension formalizes this. At the twist bifurcation, theoretical dynamics split. The scalar branch is the Maxwellian regime, where strains simply add, much like helium-4. The spinor branch utilizes Pauli matrices to preserve phase relationships, opening the non-Maxwellian regime, mapping to helium-3. This mathematical split aligns with established physical behavior, providing a precedent for the 20 series experimental design. The 20 series adjudicates 4 hypotheses. H0 is the classical resonance null, while H1 models the Maxwellian thermal limit. H2 models the non-Maxwellian regime, predicting faster mode locking under directed drive. Full adjudication requires testing H3, the memory-dependent regime. This is the most discriminating hypothesis. H3 predicts that physical coherence memory will vividly manifest as trial-to-trial training effects and history-sensitive mode selection across physical tests. This prediction is quantified by the training law, an exponential formula that maps the expected reduction in locking time across repeated trials. To isolate this effect, the experiment employs a graded memory reset hierarchy. These controls are designed to eliminate the influence of simple mechanical settling. A level 3 reset requires power cycling the electronics, unclamping the plate, rotating it 90 degrees, and reapplying a fresh visualization medium. If the exponential scaling of the training law is observed after a level 3 reset, it indicates the presence of structured coherence memory. A vulnerability in any experiment is that an observation might be an artifact of a specific piece of hardware. Addendum 20.1 addresses this by running the protocols across a 6-platform memory gradient. On the far left are 2 zero-memory negative controls, an acoustic resonance tube and an ideal LRC circuit. If training effects appear in these zero-memory controls, the methodology is flawed and the hypothesis fails. The 2D Chladni plate sits in the center, providing a substrate with moderate, testable memory capacity. On the far right is the calibration anchor, a ferromagnetic toroid. Ferromagnetic hysteresis is an established reality in condensed matter physics, with a known accommodation rate. The ODTBT framework must align with this established magnetic data to be considered a valid model of coherence memory. To validate the framework, the observed exponential training must scale monotonically across these platforms according to their physical memory capacity. The 20 series architecture connects thermal limits, the hypothesis matrix, and a 6-platform hardware gradient. While the 10 series establish the boundary of memoryless thermal identity, the 20 series apparatus crosses that boundary using directed probes on history-bearing materials. Addendum 20.1 publishes this experimental design and its predictive formulas in advance of data collection. The objective is to determine if the memory gradient produces the predicted systematic scaling. Both positive validations and null results will advance the framework, and both will be published rigorously. In advancing systems theory, the value lies in asking a mathematically precise question that can be tested against physical hardware.